Okay, so we're going to look at the second half of this lesson set, about 19, 20 problems or so. I thought it was important to start talking a little bit about concept a little bit more. So given a rate of change of 2x, integrating that gets you x squared. I think we've done enough lesson sets to hopefully see that. And so another way of writing x squared is actually finding a coordinate and I guess just look at that for a minute and take a gander at it and see if you can tell me why x equals 3 gets you 9. Well, accumulation under a curve, under 2x, we're going to look at it over here in a second. But what happens if x is 3? How much area is going to accumulate? I don't think any. And so if we want a 3 to match up with a 9, then we write a 9 there. Now let's actually look at the area under 2x because it's easy to work with. Okay? So here's y equals 2x. And if I move over 1 unit, my altitude is 2 times 1, 2. And that's triangle. It's a right triangle. And 1 times 2 is 2. Cut in half is 1. And guess what x squared is at 1? 1 times 1 is 1. What if we went over 2 units? Doubling it gets us 4. 2 units of width, 4 units of height, gets us 8, and cut in half is 4. And guess what 2 squared is? It's 4. And we'll do one more on the right. If we go 3 units, we double that, we get 6, 18, cut in half is 9. And x squared, 3 times 3 is 9. Now what happens if we look from 0 to the left? Well, I go back 1 unit, I go down 2 units, and a negative times a negative, still a positive. And cut in half is 1 unit. Boom, there's your 1 unit. And if we did 2, that's positive 8, cut in half, positive 4. Boom. And I think we get to see that happen. All right, now let me get a little eraser going here. Okay, I should have that ready the next time. All right, so that's just a little something to think about and to hopefully see. And let's look at some of the statements that we have been introduced to, and let's see if we can make some sense out of them. So let's just pick a random value for x. I picked 4. Then 2 times 4 is 8. And if I said dx was represented by 0.001, and remember dx could have a lot more zeros in it. And it's like a Phillips head screwdriver. Right? The smaller the change we make in x, the more accurate we can look for rates of change. And so 2 times 4 is 8 times 0.001. Is it 0.008? Well, let's take a look. Let's take a look at the slope of x squared, doubling the x value. And with some of the table values we've worked with extensively in the Algebra 1 videos. 4 squared gets you 16. 4.001 gets you 16.008001. And so if I divide by 0.001, I get a representation of rate of change at 2 coordinates close together. And that looks to be about 8 to 1. But if I put more zeros in, like 5 decimal places, it's even closer to 8. Which means the smaller this change, the more accurate the calculations. And I think that's important to see. All right, so one of the problems on this lesson set is to write x cubed minus 2x plus 5 as an integral expression. Well, one thing we definitely need is to shut off this light because I think that's getting us reflections. Let's see. Let's see if that's better. Hopefully so. I'm playing around here. Well, if we're going to nail this function, we got to have a coordinate. How about I put a 1 in? A 1 gets us 1 plus 2 is 3 plus 5 is 8. Can you do it? We want a 1 to get an 8. There we go. And if I let x equal 1, no area is going to accumulate. And I'm going to get 8. But we need to get under what curve? Well, we need the derivative, which is 3x squared plus 2 dx. And that's a dy statement like we looked at just a moment ago. And so if we integrated dy on the left side, when you integrate dy, it's being multiplied times 1, you actually get y plus c1. Over here, you're going to get a c2, and you bring them together, and you can just leave c on the right-hand side. All right, so this is how I think you can write them now. Years ago, when the first graphing calculators came out, didn't like seeing the variable used in different places like that, and we used to have to do dummy variables. I don't think you have to anymore, but I haven't been around it enough to say that with a high degree of certainty. But I'm pretty sure that if you put x in here and you went to one of the graphing apps, I'm pretty sure it'll graph x cubed plus 2x plus 5. It's a more complicated area under the curve to kind of follow, but doable. So there's one of the problems. I'm not naming what these numbers are anymore. I'm just saying I want the equation of a line tangent. A lot of repetition now from 5 and 6, calculus 5 and 6 lesson sets. A lot of repetition. So y equals 2 times the absolute value of x. And I want to know how it's changing at x equals negative 4. All right, and every time I ask a question, you pause the video and you try it. Well, I know what this graph looks like, and that's what I said you should do when you're working with absolute value. Draw a picture, and I can see that 0, 0 is the vertex, and I can see that if I put negative 4 in, the absolute value negative 4 is 4 times 2 is 8, so I get negative 4 comma 8, so my change from negative 4 to 0 is up 4 units. And 8 to 0 is down. So I'm actually going down at 2 to 1. Don't let this arrow fool you. All right, we read graphs from left to right, and there's a constant rate of change there, and it's negative 2. I wonder if you can guess what it is on the other side. All right, so there's another problem done. We also have dy dx equals negative 4x over y. dy dx equals minus 4x over y with an initial condition of 0 gets you 10. So y of 0 gets you 10. So we're going to integrate this. We're going to look at the area under the curves. I'm going to move the y to this side. Multiplication becomes division becomes multiplication, and division becomes multiplication on the other side as well. All right, so this is going to become y2 over 2. We're going to move our c's to the right. This one's going to become minus 2x squared. I hope you can see, take a derivative, gets you that, plus c. 0 gets us 10. 10 squared is 100 divided by 2, so that's got to be 50. And if we move things to the right and double them as we do it, we're going to get positive 4x squared plus y squared equals 100. That's an ellipse. And if I want to know how the function is changing at any instant, I have a formula over here that can tell me what that change is, what that slope is. All right, so there's that problem. Hopefully you're following, because we did another one or two like it previously. We can look at the limit as x goes to e. What's the limit as x goes to e of the ln of x minus the ln of 1 over x minus e? Well, L'Hopital tells us that 0 over 0, we could do something quick mechanically, but can you see conceptually what's going on here? This is the function in question. We have x, we have the ln of x, and at e, the ln of e is 1. So this is like saying x2, and this is like saying y2. I'm sorry, x1 and y1. And this could be any ln value. Let's do 3. Then this is the ln of 3. And I put these in a calculator because they're pretty close together. It's going to approximate the slope of the tangent. And e from 3 to e is a change of about 0.29. Right? E 2.71 to 3, 3 to 2. About 2. That's the change in x. And ln of 3 is approximately 1.1. It's closer to 1.09. But we'll use 1.1. Our change, 1.1, is 0.1. Okay, this number's pretty close to 0.3, so let's just call it 0.3. 0.1 divided by 0.3, multiplied by 10. We get a 1 to 3 ratio of change by doing that, average rate of change. But as I move this number towards 2.71, let's make it 2.9. Let's make it 2.8. Let's make it 2.72. And then if I were to throw that in a calculator, I'd even be closer to the derivative of the ln function at e. And so what is the ln of e? We know it's 1. And what is the derivative of the ln of x? 1 over x. So let's look at 1 divided by 2.71. Okay, let's multiply by 10. Let's just call it 10 over 27. Are we getting close to this? Are we trending towards it? Yeah, and I'm using some just gross approximations for that exponential, or for the inverse of the exponential function e to the x. All right, and so let's graph ln of x. Doesn't hurt. X equals 0 at asymptote. Okay, where are we at e? The ln of e is 1. Does it look like we might be going up at a 1 to 3 ratio of change? I hope so. Right, so trying to get a little numerical approximation sometimes gives you a sense of, you know what, these calculations work. All right, so now we're looking at a cubic. Minus x cubed plus 27x plus 25. All right, we'll do it with calculus over here. Minus x cubed plus 27x plus 5. And these are in graphing form, okay? So b, this is a, b, c, and d. Notice there's no b term, 0x squared. All right, so minus b over 3a, one more time, is 0. Put a 0 in, you're at 25, and you're going up at 27 to 1. If you want to understand why that all works, you got to go to the cubic playlist, look at completing the cube, look at the geometry behind the problem, and you'll get a chance to see how to put cubics in graphing form. So now that I know that, then I know that my local max, so first off, I know that the function looks like this. And so the local min, max, which one did I want? Let's go for max, which is what we did in the last lesson set. I know the slope there is 0, all right? And I know that at 0, I'm at 25, or I'm at 5, excuse me. I'm at 5, going up at 27 to 1. Okay, and it's the interchange of the linear function and the cubic function that you'll see in the playlist, the cubics playlist, that will explain that I know the x values, and I'm going to say h, the horizontal change, positive in that direction. To get to the minimum, it's negative in this direction. So I start from minus b over 3a, which I'm calling h, 0 plus minus the square root of, when does 27 to 1 get offset by the cubic? So going up 27 to 1 means I'm going to use the opposite slope, and I'm going to divide it by 3 times a, which is negative 3. And now I know that over here at x equals 3, I get a maximum value. And when I'm talking about values, I'm talking about y's, not x's. Okay, so I'd actually have to plug in 3 to get the maximum value here. Is it hard to do? I don't think so, so let's plug it in. 27 minus 27. plus 27 times 3. So I can take one of the 27s away and multiply by 2. 54 plus 5, 59 gets me the maximum value. Now if I'm using calculus, I have to prove it's concave down. All right, so let's look at concavity very quickly here with x cubed. First derivative is 3x squared. Let's make sure you can see this. Of course you can't. So everything I've been doing, did you see that enough that I had to start this video over again? God, it's so hard to work outside of the classroom. All right, so you had this picture. Didn't see this completely. Yes, you did. All right, so I guess we're okay. So I got to put this down a little bit so you can see what I'm writing now. Oh boy, that's difficult to see at all. All right, so let me do it over here. So we got x cubed, which we know looks like that. All right, and we got 3x squared, which measures the slopes at any instant of this function. Now, what do you notice about 3x squared? I notice that, for the most part, it's always positive. And if my slopes are always positive, the first derivative is always positive, my parent function is always going up. And if I start from the left, my finger tends to always go up, except at 0. And I seem to get a change in concavity here, from concave down to concave up. So let's look at the next derivative, which is 6x. And if I graph 6x, I'm always increasing. So if my second derivative is always increasing, then it implies that the first derivative is always positive. All right? But the other thing is, I go from second derivative, I go from negative to positive. And when the second derivative is a negative, that's when I'm concave down. And when the second derivative is positive, that's when my parent function is concave up. And you're going to hear that for a month. Every time we do a lesson set, I want you hearing that, so that it becomes working knowledge, not just memorized knowledge for a test. So now, let's start with y equals. Let's go y1. Sorry, y prime. So y prime minus 3x squared plus 27. Let's set that to 0. And you do that in your head. You're going to find plus or minus 3, which is what we said those local max and local min x values would be. And then you'd have to plug it in. To prove that you're on a concave down interval at x equals positive 3, you need the second derivative. And the second derivative is minus 6x. Minus 6x looks like this. And at x equals 3, I have a negative second derivative, which means I've got a concave down situation with a slope of 0. And that proves that we're at a local max. All right, I'm running out of ink. Don't like that. Do I have another pen? Yes, I do. Next time I do a video, I figured out how to use the back side of this thing. And I had a laugh doing that. So let's write x cubed minus 2x plus 5 as an integral expression. X cubed minus 2x plus 5. Well, this is much better. Of course, you got to be able to see it. There we go. X cubed minus 2x plus 5. How do I write that as an integral? Well, you're pausing the video. Well, I can see a 0 gets me 5, so I'll take that. That's a gift. All right, and now I need the derivative of this, which is 3x squared minus 2. And I got to hit those altitudes with little bits of width. All right, that gives me, 3x squared minus 2 looks like this. And if I do an altitude there, then that altitude is coming from 3x squared minus 2. And if I give that altitude just a little bit of width, dx, 0.001, and I do an infinite number of those, then I'm going to accumulate area from 0. First it's going to be negative area, then it's going to be positive. And if this is a first derivative, I'm increasing from 0, so therefore if my derivative is increasing, then I'm on a concave up interval. And over here, I'm on a concave down angle. All right, boy, it's hard to keep track of that. All right, so what happens when I put a 0 in here? No area accumulates and I get 5. Okay, and then the others I'd have to do some calculations for. But maybe we do this out. All right, so x squared up 1 divided by that gets me that. Minus 2 integrating gets me that. I'm going from 0 to x, and then I'm adding 5. Doesn't hurt. So plugging x in gives me x cubed, so that these are just simply placeholders. Could have called these any letters I wanted. And now I'm going to do this. So when I put in it's more complicated. I put an x in, I get x cubed minus 2x. When I put that in, when I put a 0 in, I get 0, 0, 0 minus 0, and then I add 5. Okay, so what do I get? What I asked you to get me. That function, written as an integral expression. Could have done it in an infinite number of ways. All it depends upon is where I decide to start measuring from. Okay. Interesting, very interesting stuff. So let's look at the ln of x, and let's write 3 left-hand rectangles. 3 left-hand rectangles. So here's 1. So if that's 1, that's 2. I gotta make this. Gotta make 1 appear a little bit sooner. All right, so there's 1. So that's 2. That's 3. I gotta get to 5. That's 4. That's 5. And I'm going to use 3 left-hand rectangles to measure from 2 to 5. Well, that's nice because each width is going to be 1. So there's my first rectangle. I'm taking the ln of 2 as a height. And if I multiply it times 1, then this area is the ln of 2. This area will be the ln of 3. And this one here will be the ln of 4. Okay, so this was the ln function. And each width is 1, ln of 2, ln of 3, ln of 4. Left-hand rectangles. Now let's do 3 trapezoids. 3 trapezoids, a little bit harder. I didn't pick the greatest one to do with widths of 1, but they look like trapezoids anyway. All right, but they're going to be a slight underestimate. So I need the width divided by 2 times the altitudes, and the first altitude uses ln of 3 twice. The first trapezoidal area uses ln of 3. Right? So does the second trapezoid. It uses ln of 3. So all the ones in the interior get used twice. The one on the outside gets used once, and the one on the outside gets used once, and the ones on the inside, so that was a 5 I guess, get used twice. So 2 ln of 3 and 2 ln of 4. And that is something we're not going to calculate. We're just coming up with the calculations. And so width divided by 2, altitude on the left, altitude on the right, and double all the altitudes in the middle. That's your general framework. And if you hear that for another 36 lesson sets, I got a good feeling at final exam time. All right, so y equals x and y equals x to the 4th. We're going to find the area bounded by these curves. All right, so we have our x to the 4th function, our y equals x. So where's the bounded area? Right here. And we have to define that altitude. And we also have to find the points of intersection. So we set x to the 4th equal to x, which means we subtract x and set it to 0. We factor out an x, and we get x to the 3rd minus 1. And we can see that we intersect at 0, 0. we will be doing intersections with respect to y at some point. So I'm giving you the x and the y. And it also passes through 1, 1. So how do I define this? I need a number minus another number. Okay, so let's pick a half. This looks like it's halfway. So what is that altitude? Well, I know the top function is x. So at 1/2, that altitude is 1/2. And I know the bottom function is x to the 4th. So what is that altitude right there? What is that distance right to that dot? 1/2 times 1/2 times 1/2 times 1/2 is 1/16. So that's one altitude. And what would dx be? 0.1. That would capture a little bit of area. And if I did that, if I did 10 of those, I'd have a nice approximation. But if I did 100, that approximation would be 10 times more accurate. And if I did 1,000, boy, I got a feeling I'm getting rid of a lot of error. And if I did 1,000,000 of them, I think I'm getting really close to an exact value. All right, so how do I measure altitude? Well, usually when you do altitude, when you're a little one, they put a little mark on the wall and they measure it from 0. Okay, but we're not on ground level. We're just a little bit above. So this altitude would be 1/2 minus 1/16. All right, but from a standpoint of all of those altitudes, well, top minus bottom. And top minus bottom, let me do it at the top here. My top function was x. My bottom function was x to the 4. And I am going to give those a little bit of width, so I'm creating a rectangle. And I'm going to add them all up from 0 to 1. Now, since we've got 0, we'll calculate this one because it won't be hard. We don't have to drop 0 in. We've got x squared over 2. We've got minus x to the 5 over 5. And we're going to go from 0 to 1. So I really have 1/2 minus 1/5, which is 5 minus 2, 3/10. A little bingo, bango, bungo. Does it look like this might be 3/10? Well, let's go all the way over to 1 and make one big rectangle. 1 times 1 is 1. That's the whole rectangular area, but I'm only looking at that much. Does that look about 3/10? I hope so. All right, so we're finding areas bounded by curves. So if one rate represented Grandpa's rate, let's say Grandpa's rate is y equals, or Grandma, I'll make Grandma's rate y equals x, Grandpa x to the 4th, right? So those were rate functions. Then over time, your rectangles are measuring rate times time, which is distance. So maybe they have a fight, and Grandma takes off at y equals x, and Grandpa takes off at x over 4. And, you know, initially he's going slower, but as she gets away from him, he gets like scared, anxious, and decides to pick up his speed until he matches her speed. So what do we know when he matches her speed? That area, 3/10 of a mile. That's how far she got ahead of him. All right. Love those grandma stories. Now we've got a limit. We want to use a limit to express the rate of change of e to the x at x equals 1. Now, can you write a limit expression? Well, there's actually two ways to do it. One is to see e to the x, and I know 1 gets me e to the 1, which is e, and I could start here at 2, that would get me e squared. But that's an average rate of change. This is somewhere a little bit bigger than 7, minus 2, let's call it 5. You know, that's a 5 to 1 average rate of change, but I got a feeling this is changing differently at x equals 1 because we know what y prime is. Y prime is plugging a 1 in, so you're going up at 2.71 on e to the x at x equals 1. So here's our e to the x at x equals 1. We're at approximately 2.71, and this is going up at 2.71. So how do I write the limit as x goes to 1? Well, that's not hard. That's the limit as x goes to 1. Well, there's my x. It's getting closer to 1. You know, I'm looking at 1.001, and that x is even closer, and so this is e to the x. Well, how do you compute slope? Well, e to the x minus e over x minus 1. So there's your x equals 1. Right there, there's your first x. There's your first y. This is y1. And this is a generic y2, x2, right? And so we got our y2 minus y1 over our x2 minus x1, right? And we also have what? From 2 to 1. We have a horizontal difference. And what happens when we move to 1.001? We're letting that horizontal distance go to 0. So I could have put an h here, and I could have said as it goes to 0, what do we have? We have this x is very close, so we have x plus h. We have 1 plus h minus 1. Here, I finally said that right. And so what is your x2 minus your x1? Just h. And what do we get when we put 1 plus h in for x? We get e to the 1 plus h. All right, so we can change this to e to the 1 plus h minus e. And we have 1 plus h minus 1, just h. And that's another way to express the derivative of e to the x at x equals 1. Because what is, well, I guess you can see it. I don't think I can say much else other than what I just said. All right, so again, a consideration of a concept that's important, but I firm believer on 4 days, and this is the second, right? Each lesson set is really 2. Lessons 7 and 8 were 1 day of work in a classroom. Okay, but I'm breaking it up here because it seems like it's, initial discussions are taking too long. So let's see, where are we at now? What have I also got here? I've done that, I've done that. All right, let's look at f prime. And let's have that equal minus x times x minus 2 squared times x plus 3 to the third. All right, and we want to know something about big F. So in that series of functions, that's your second derivative. Okay, and what do I want to know? Do I want to know when this is concave down? Yeah, that's what I want to know. So when is the second derivative concave down? I'm sorry, when is the parent function concave down if we've been given the second derivative? It's when the second derivative is negative. So we got to be able to graph this. So negative 3, sign change because it's odd. Add 2. Hopefully you've done this work in your Algebra 1 to Trig videos where this gets explained how to graph. And go to the playlist perhaps. I don't know if I did one of these graphically in a playlist. But maybe you can go to some of the early Algebra 1s. I'm sure I introduced it at some point in the 1 to 50. So 0 sign change at 0. No sign change at 2. Here I was talking too much. So I like to use a dot, right? This is going to have x-intercept at 2, and it's going to take on the look of x squared at x equals 0. So if I put in a big number, I can see that I'm going down, right? Big positive, big negative. So I'm going down, and then I'm getting sign changes. At 0, I'm getting a linear sign change, and at 3, I'm getting a cubic sign change. So that's what the graph looks like. When am I negative? From negative infinity to 3, so this area here, this interval here, is so negative infinity to negative 3. Big F is concave down. Union, how about I say, it's got to be 0 to 2. At 2, I'm flat, but it's not concave down at that instant. So another union, 2 to infinity, and I hope I have this down low enough you can see that, barely. All right. Well, this marker's going now too. All right, so negative from 0 to -3, union 0 to 2, 2 to infinity. Okay, hopefully that's stated well enough. What else is over here? Anything else I haven't done? Is that enough for today? Oh, I should do an implicit differentiation. I'll make one up on the spot because I know we did one 2 lesson sets ago, and I want you to get that repetition. I'll keep everything positive here. So let's say that I have the relationship x cubed plus 2x y to the 3 plus y to the 4, and let's say that equals 50, and I want to come up with a function or at least a formula that gives me slopes at any instant of this curve. I got no clue what that looks like. But I've got y equals, I know, so I'll do this. I'll do it this way. So this is 3x squared dx. If I take the change, which means that on this side I could move the 3x squared over. So just to show you that you could trim down how long it takes you to do these, you could really just write your answer. All right, so now I got a 2dx times y cubed, and then I have a 2x times 3y squared dy plus 4y cubed dy equals 0. So that's the differentials. All right, so now when I divide by dx, we can see that one's going to cancel. That's why I could immediately move it there. We can see that this one's going to cancel. So I'm going to get 2y cubed on the other side. And we can see that this one gets me y prime. All right, and I'm going to multiply on the left, so that's going to become division on the right. 2x, 3y squared comes 6xy squared. Same thing over here. If I divide by dx, so dividing 0 by dx doesn't matter. So I've got a multiplication by 4y cubed, so over here I have a division by 4y cubed. And now I have a statement based on x's and y's that tell me how this thing is changing at any instant. All right, I'm going to have to get some new markers. These didn't last too long. Okay, so one more problem here I haven't done. Did I do it? I think I might have. Dy dx equals, that's my short-term memory now. Cognitive decline continues. Hey, that's good enough. All right, I'll pick it up again another time. No, I'll do this one. I don't think I did it. So dy dx equals minus 4y over y, minus 4x over y, excuse me. I'll just do it quickly. And with an initial condition of y of 0 equals 10. All right, so I'm going to separate the variables, y dy, and I have a phone call. I'm going to ignore it. And then I have minus 4x dx, and a 0 is going to get me 10. All right, so this becomes y to the 2 over 2 equals minus, so this is going to go up 1, and divide by that, minus 2x squared, and that's going to be plus c. So if I put a 10 in right now, a 0 right now, I want to get c, so 0 gets rid of the 2x squared. 100 divided by 2 is 50. And now I'm going to multiply everything by 2 and move things to the right. So I've got 2x squared plus y squared equal to 100. And so that was an ellipse. All right, if I did that twice, doesn't hurt. Repetition helps. So if you pause the video, you should be able to do it yourself if I'd already done it. All right, so coming in under 40, that's good. And let's see. We'll pick it up again on Wednesday. You have a day off, and then we'll do Thursday, Friday. And so feel free to go to the calculus playlist, see if some of the concepts are explained there. All right, enough for me. Have a good day, and I'll post this tomorrow.